quite an honor to have been asked to speak at this session and honor of Shiraz. I guess I probably have the dubious distinction of having known Shiraz the longest of the folks here. We actually, as he said, were graduate students back at Illinois together in 1971. And I graduated in 73 with master's, went off to the Army for a short while. Shiraz stayed and got his PhD. But over the years, we've circled back across projects, both as colleagues at the same firm. We've been on projects both on the same side of the fence, other sides of the fence, and working on technical committees, and oftentimes being a mentor to each other. Probably Shiraz more to me than me to him, though. And what I want to talk about today is a rather mundane topic. It's the strength, variability, and mixed design process. And I think we can see from some of Ray Rawlings's presentations, these are things that oftentimes maybe get overlooked as to their importance with things. But the data I'm going to talk about today comes from two major airfield paving programs at two different airports. Both of these programs each had well over 1 million cubic yards of concrete, fairly large contracts ranging from up to as much as 450,000 cubic yards on a single contract, and obviously thousands of sets of beams for strength. When we look at the mixed design process, there are three fundamental things that I tend to look at, and one that most people look at is strength. And typically beams are cast to the concrete mix in production, tested in Flexural, whether it's center point loading or third point loading, to measure the flexural strength. Third point loading is the one that's used primarily, but it's a key point. You need to remember which test you're talking about when people are talking about the results. The center point test will give results that are about 100 PSI higher than the third point test. And obviously some of this is primarily due to the maximum moment in center point only occurs at the center point. In the third point load process, that maximum moment occurs across the middle third of the beam, and hence there's a greater probability that you've got the low part of the beam in there. So one of the things that people like to do for fixing strength problems is add more cement. However, that presents other problems. You may gain strength, but you also may end up with more shrinkage, more cracking and problems. So fixing one problem oftentimes leads to another problem. The second issue you tend to look at is workability. How well can I place the concrete and consolidate it properly? Sometimes we find that the concrete's too stiff. We get tears in the pavement, and that gets finished over. People don't know it's there. And every now and then you take a core, which just happens to be lucky, and find the tear. I think today, as we move forward, looking to the future, we've got non-destructive procedures that can help us look at some of these issues without having to cut the concrete apart to find them. Other issues, you may find the concrete gets, quote, too wet. This is a joint process that I would never use today. It's a keyway longitudinal joint, and you can see the black line there illustrates where the keyway was supposed to be. It's not there. It's actually over there, and you can see the dowel bar off to the right there also. So issues that you have, oftentimes, well, add more water, the mix will be good. Well, again, it's a two-edged sword. You may get a more workable mix, but you may end up with more shrinkage and more cracking. The good thing about slip form paving is it tends to be self-policing. If the concrete won't stand when it comes out of the extruded finishing, then obviously it's too wet and the contractor needs to get that fixed. The one that I consider most critical and crucial is durability. And we look at that, there's a whole host of factors. We don't have time to go into these today. You can spend whole courses on them, but things like gradation, geology, particle shape. And this particular site here, this is not a paving project, but I include it just to show some of the issues you get with problems with mixes. This is a ready mix plant for produced concrete for a 50-story high-rise structure in Shanghai, China in the late 80s. And it was a 1-hour cab ride out to the plant site from the project site, which presents problems in and of itself. But when you looked out over the aggregate stockpiles for the coarse aggregate, you saw all kinds of different colors and all mixed up together. And it's been my experience, lighter colored aggregates tend to have a lower specific gravity than darker colored aggregates. And so if you've designed a mix on dark colored aggregate and you're putting in light colored aggregate and not adjusting for the differences in gravity, you start to change the yield and the effective cement contents and issues that come up there, to say nothing of issues with gradation of the different sources. And asking the batch plant operator how he accommodated all this, he said, hey, I can get aggregates from 200 different quarries. Whatever's in the stockpile is what goes in the mix. And so I kind of walk away shaking my head thinking, we're going to build a 50-story high-rise building with this. But to my knowledge, it's still standing and things have actually ended up okay. Also, we have things with mineralogy. You may have pyrite, alkali silica reactivity issues, freeze-thaw, decracking, flat and elongated particles, friable particles. And sometimes you see, you think you got gold in your aggregates, and no, it's actually pyrite. And you can see it where it's little nodules to this. Particularly if it's covered properly, that will not be a problem, but it is prone to staining and expansion issues. So you need to be careful of all the different minerals that are in. So when you look at the 3 factors, strength, workability, durability, as I say, I consider personally durability to be more critical than any of the 3, and particularly more critical in strength. I can have very strong concrete that's not very durable, but if I have durable concrete, I'll probably have adequate strength. So keep these in balance when you're looking at starting the project, getting the QA, QC people oriented. But the problem we have is strength is still a major factor in pavement. It's what engineers specify. It's what owners base their pay on. And as a contractor, when I'm talking with contractors, well, they want to know what strength is needed to get 100% pay on the project. Obviously, they don't want any strength penalty payments, reductions. So look at, well, what strengths required in the lab designs, and also what strengths required in field production. And you're going to see a drop typically from the lab to the field because the field is not as controlled, both in ability to measure materials and control the environmental conditions. So in looking at this, I thought I would take a look back at the past and see what's been some of the history of strength requirements in concrete paving over the years. And if we go back in 1948, the Civil Aeronautics Administration published an airport paving manual. And this is actually older than I am, believe it or not. And they had 2 charts in there for concrete pavement thickness. And these were pretty simple. If you had the pavement use, whether you had runways, taxiways, or aprons and runway ends, you went into the particular chart appropriate. The subgrade was based on stipulated gradation, Atterberg limits, and whether you had good drainage or poor drainage, and whether you had no frost or severe frost. And then obviously the wheel load. So with those 3 factors, one could design the pavement. And when I think about that, you look at the top, the top is concrete, the bottom half is subbase, and we won't get into that. The concrete thickness comes out, but it's interesting to note the subgrade classification in that manual only impacted the thickness of the pavement by about 1 inch in terms of the concrete. But the use, i.e. the amount of loading and frequencies, could have an impact of up to 1 to 4 inches. So the subgrade didn't have a whole lot of impact. Now, when I look at this, what's missing? Concrete strength. Concrete's not a variable in this design chart process. And when you look through the manual, what you find is strength is specified in the standard specification for construction, also dated 1948. And I don't have a copy of that. I located lady in Maine who purports to have a copy of it, but it's buried in boxes, and a month of searching still hasn't turned it up. But I suspect that it probably specified a lower limit for strength. So if we fast forward to 1974, this is about the time that Shiraz and I actually got into the practice of doing things. The 1974 Pavement Design Manual from the FAA, and I just picked out two charts out of this just for illustration. There's numerous charts in this manual, but what we see, concrete strength now is a factor in design. We have, and it's also with a factor of safety. So you take your design strength, put a factor of safety on it, depending on how many repetitions you're going to have and the like. And so you can go into your chart there. Subgrade strength now is not based on classification. It's based on actual strength test, the plate load test, which yields a K value, and still obviously the gear type and the wheel load. So with those three factors, one now can look at the pavement. And it's interesting if thinking back to, okay, what strengths do we need? If we have a concrete with a flexural strength of 650 or concrete with a flexural strength of 750, and we apply a factor of safety of 2 to that, we have a nominal subgrade of 100 PCI, a dual gear with a gross weight of 100,000 pounds. We go through that, what we find is there's still only about 1 inch difference in thickness of the concrete, even with a 100 PSI change in the design strength. So think about that. We get all bent out of shape sometimes on projects over small changes in the flexural strength, and yet in the old charts, changing the strength by 100 PSI had almost very minimal effect on the concrete, the thickness. The mixes in the 70s, typically 1/2 inch to 1.5 inches for slump if you were going to be slip forming, and that's what the big projects typically use. And air content was specified between 3 and 7. Important point here on air content, Ray talked about it in his discussion of the 4% versus 6% and like. But what I found over the years is for every 1% change in air content, I change the flexural strength about 5%. So if I'm having strength problems on my project as a contractor, I just say, hey, lower the air content. And you'd say, and so the strength probably goes up, but guess what? That may create a durability problem. I may be impinging down on the problems with freeze-thaw durability potentially. I may be, because of the lower air content, needing more water for workability. And when I put in more water, maybe I create shrinkage cracks. So things have changed a little bit over the years. And at that time, flexural strength, you made 2 beams for each 150 cubic yards of production concrete. You tested one at 7, one at 28. And the moving average of 5 tests had to stay above the design strength. And no more than 20% of the beams could be less than the specified strength. The issue with that was it wasn't clear where that 20% could be. Is it one beam in every moving 5 calculation? I could have a couple of 640s, a 680, a 690, a 700, and still be above my 650, but I'd have 40% failures. And they only fail by maybe 10 PSI. And remember, 100 PSI in this design only affects the thickness required by 1 inch. So you have to think about what is it you're trying to do here. The pavement also was paid based on thickness, and it was only a deficient thickness issue. If the contractor was within 0.2 of an inch, 100%, and you can read the numbers going on down. I always like to draw a picture. It helps me look at the words a little easier. And if the contractor got more than an inch shy in thickness, then it might be removed and replaced. And that's a triple problem for the contractor, because if you come in time to remove it, he's had the cost of putting the concrete in, the cost of taking the concrete out, and the cost of putting it back in, to say nothing of delays to the owner and so forth. And I've been on projects where project delays actually sometimes have threatened to put the bonds into default. So you have to think about what's the financing of a project when you're dealing with all these things? Okay, and there was no benefit for extra thickness. And so flexural strength, there also wasn't a clear penalty. We weren't sure what 20% could be low, where that could be. And there was not a clear penalty for strength. Jim Tuttle, in the mid-70s at HNTB, when we were working at the Atlanta airport, developed at the bar one night a little formula. And what it was, he said, we'll take the measured thickness in the flexural test and we'll multiply it by the actual thickness from cores divided by the design thickness, and that ratio will be squared, and come up with an adjustment when needed for that extra thickness. Now that comes into play, help out the flexural strength. And one might say, well, that's pretty helpful to the contractor. Well, if you remember, sigma equals MC over I, supposedly. I is 112 BH cubed, so one could argue that you should actually be looking at a cube of the thickness here. So if you have a 16-inch design, you put in 16.5 inches, the concrete strength would be up to about 40 PSI from the measured. And if it was 17 inches versus 16, it would be up almost 84 PSI. There again, 1 inch, something in the range of 100 PSI. It's just something to keep in the back of your mind with that. But it's a two-edged sword. If the strength is low and then the thickness happens to come in low, you have a problem. And one time I was on a project, it was an Air Force project. Contractor had put in concrete, he had low strength in his beams. We went in, did all kinds of testing, tested compressive strength, tested split tensile, and concluded that yes, the strength was low, but he had put in 12 3/4 inches instead of 12 inches. And when you analyze the results and the design charts with the additional thickness, it indicated that the pavement should actually perform. And so we went to a big presentation with a base civilian civil engineer, talked about all the issues and how, yes, it was lower strength, but it was thicker, so it should perform okay. And at the end of that 4-hour presentation, that base civilian civil engineer said, oh, you meaning instead of giving us 12 inches of bad concrete, he's given us 12 3/4 inches of bad concrete. So sometimes communication is hard to get across. So if we fast forward to 2018, what we see is the standard specifications. Now concrete's still based on strength, but it's gone to a lot. The concrete's accepted on a lot basis. And I think the FAA went to that in the 90s. That's a big change. Suddenly that amorphous 20% low breaks is now well defined in terms of a lot, and 90% has to be within limits. And we'll talk a little bit about that. And thickness, grade, and some other issues get looked at. So you look at a lot is about 2,000 cubic yards, and there's 4 sublots per lot of about 500 cubic yards is the general intent for that. So there's 2 test specimens per sublot. There's a procedure for discarding outliers and the like. The strength of the sublots, the average of the 2 specimens. Typically, everyone is specifying 28-day strength. And the strength of the lot is the average of the 4 sublots. And then you have the standard deviation of those sublots to define what you're doing. And that looks something like this. You can see the sublots, you get your average, and then you get your average for your lot. And to get the 90% within limits is what's required to get 100% pay. The contractor says, well, what do I need to get in the lab mix design? I say, well, before we go to lab mix designs, I need to know what are you going to do in the field? And we look at the FAA's chart. They have this handy dandy table in the P501 spec. You look at that, your head kind of spins with the equations. But if you plot them up, you see, oh, that kind of makes sense. I can now see what I look at depending on what's within limits. And then you go to section 110, which is the process for determining percent within limits. And you have to calculate the QL value, which is merely the lot average minus the lower specification limit divided by the standard deviation. And there's an interesting little thing. If you read all of the spec, and I find like Ray, I think, said, a lot of times people don't read the specs until there's a problem. The lower specification limit, L, is 93% of the strength as specified in paragraph 501 3.3. And that makes for a 650 design, this lower specification limit's about 605. So I go into section 110, I got 4 sublots, I'm looking for 90% pay. I need an QL equal to 1.2. So when I go through that handy dandy equation, my lot needs to have the lower specification limit plus 1.2 times the standard deviation for that lot. But now my big question, talking to the contractor, is what's going to be your standard deviation in the field when you produce this concrete? How much variable is your concrete going to be? And when you look at big paving projects, contractors come in, they set up on-site central mix plants. They'll have on-site storage for their materials. And the materials may have little or no history in the use on there. So you go to the contractor and say, well, what have you done in the past on projects, even with different materials? And what does the industry data kind of show you? And what he found is if I look deep enough, I can find that for projects that had just single beam testing procedures like the 70s, typically it's 20 to 80 PSI for the contractor. Most of the projects end up between 40 and 60. So tell the contractor, we'll be conservative. We'll assume you're going to run at 60. Now I've got 2 beam sublots. So the variability of those 2 beam sublots should be less because I'm taking 2 tests instead of 1. And that reduces to about 40 PSI. And then if I look at the overall standard deviation of the lots, I've got 4 tests in the lot. So maybe I'm producing a standard deviation down around 20, 21 PSI. So for all of my concrete to get 100%, I need to have my 605 essentially, plus 1.2 times the 42, or about 655 for any given lot to get 100% pay. However, variability is such that not every lot is going to have that standard deviation of 42. They're going to vary. And so I look at, okay, I need 655 typically. I'll go for 3 standard deviations above that. So I have not much probability of failure. And so I need something around 720 in the field. Now, what do I need in the lab? Well, I've got to look at taking that down because I'm going to lose strength from lab to field. I found it's typically about 1 standard deviation. So in the lab, I need to produce about 740. So go back to the lab. Now I'm ready to do some mix design. And I'll prepare batches maybe at 3 or 4 cement contents. I'll plot the strength versus cement. And I get a nice little curve that goes up with cement. I put in more cement, I get more strength. However, that's not always the case. Sometimes when I add cement, the strength goes down. And everybody says, well, what do you do wrong? Well, I didn't do anything wrong. The reason may be what's known as material and test procedure variability. So if I look at that, when I try to look at what kind of variability, what if I went back to the lab and put up multiple batches of each mix? What would I would get a range of strengths. And we did a little case study with contractor. And remember, when you're working for the contractor, they're not interested in research. They're interested in what's the answer so we can get going. So you're always under the gun. But we looked at putting up duplicate batches of a couple of cement factors on project. And we see that within 9 beams, where we tested all of the beams at set 28 days, we could have a range from high to low of 90 PSI, yet the standard deviation of that batch was only 29 PSI, pretty low. And if I happen to pick the high 3 or the low 3 beams, I could get anywhere from 655 to 713, and going across the page, you can see. So variability comes into play quite a bit when you're looking at things. So if I go back and think about, well, what's really going on here? If I were to go back to the lab and put up multiple batches at multiple cement contents, I might get some things that look like this. They won't be exact because none of this stuff fits the exact normal distribution, but you can see that on average, I may get an increase in strength with increased cement, which is what people expect, up to some point where I max out the mix. However, if I only put up one batch per cement content, which is what most contractors do, I may get an above average strength on the first batch. I may get a below average strength on the next batch, and a above average strength on the third batch. And people look at that and say, well, obviously the lab did something wrong. No, it's just which particular rectangle on that distribution did you happen to get at that cement content? So what I try to tell contractors to do is, look, go in here, we'll take the individual data, we'll regress it to get a straight line or curvilinear, whatever you want. We'll do that regression, then we'll put a lower bound on that curve at say 95%, and that's the curve we'll use to establish the strength that we need and cement content in the field. Or we can prepare multiple batches of those. The contractors really aren't interested in doing a lot of batches. And what I'd like to do most is go to the field and put up the actual mix before they get into production and do multiple batches and see what happens and what am I likely to get. And things that you need to look at, IPRF did a study they published in 2010 for precision of the flexural strength test. Their single operator, in other words, two tests by the same operator from the same batch of concrete could differ by 140 PSI. Two labs could differ by 200 PSI. ASTM's current precision limits say that the single operator is about 104 PSI, and two labs would differ by about 19% or 125 PSI. So there's big variabilities in these, and the variability of the test is basically in the same range as the contractor's overall variability. And I guess we'll get to the closing here. I would just say that in 40 years of playing around with concrete pavements, if it's been designed by a good engineer, constructed by a good contractor with good quality control on mixing and placing and batching, tested by a good agency, that I've not seen the pavement fail due to strength. The pavements almost always are an issue of workability or durability. And so just closing out real quickly here, performance engineered mixes. I know the Iowa State is beginning to look at some of those issues, controlling thermal movements. We might want to look at the nuclear industry. They require the mixes to have 0.04% drying shrinkage. That's less than a half inch per 100 lineal feet. Look at your air content. And I would propose do away with this test we have to wait 28 days for, 100 PSI on the precision, and go to something like maturity. A contractor can place $5 or $10 million worth of concrete in 28 days. So strength's not the issue, it's workability and durability. If I have those, I probably have strength, and millions of dollars in penalties on projects that I've seen, both I've worked on, Shiraz has worked on, and we've sometimes worked on together. I've seen those pavements perform well beyond their design life. So don't get wrapped around the issue of strength and get tied up in knots. And with that, I will turn it back to Kurt.
All right, great. Thank you, Charlie. Appreciate that. We have time for maybe one quick question, and maybe we'll kind of open this up to all of our speakers. I don't know how experienced everyone is or how well people keep up on some of the different specifications, but one of the questions is what improvements are needed for the current FAA P501 spec? So Charlie, I don't know if you have any comments, or Ray or Shiraz, if either you want to weigh in, please do so.
Well, I think the comment I made at the end of, let's look at getting rid of the flexural strength beam test. We can do those things in the lab and establish the mixes, come up with the maturity relationships, and then let's control the concrete for payment and acceptance in the field with maturity. We can get results quicker than 28 days and quit messing with a test that's got a tremendous range of variability. That would just be my thought.
All right. And it looks like Ray is turned his
I agree a lot with what Charlie's been saying, is that almost never is strength your real issue in pavement design. And we get wrapped over and over again over how to measure it and what does it really mean. I like the idea of maybe going with maturity. I hadn't thought about that in that one before, but I think that's got a lot of promise.
All right, great. Shiraz, anything you want to add?
Yeah, the only thing, at least at this time, is we still have an issue related to consolidation of the concrete, at least in the airfill side, because of the thick layers we are placing. And we still haven't developed a very reliable method or a non-destructive method to assess the consolidation, aggregate segregation, and the surface, mortar-rich surface thickness, and so forth. So that's where P501 is lacking in addressing it.
All right, thank you.